Oh, good. Now we're ready. Yeah, so I'm very happy to introduce the next speaker, Yairon Cid Ruiz, and he'll be telling us about primary decomposition with differential operators.
Okay, so first of all, I would like to thank the organizer, Jack and Luis. It's a great pleasure to speak in this Congress. For quite some time, I've been working in trying to understand primary ideals with the use of differential operators. And now I want to present like how to describe any ideal with the use of differential operators. Everything here is joint work with Bernd Strumfels, and we introduce a notion that we call differential primary decomposition. We want to do primary decomposition with the use of differential operators. That's the title. So the beginning of everything here is this beautiful theorem by Victor Palamudov that if you are in a polynomial ring over the complex numbers, and then you have a prime ideal, and you have that Q is a pre-primary ideal, then Victor Palamudov, he showed that there exists a bunch of a finite number of differential operators, A1 until AT, inside this bialgebra, and he calls them Noetherian differential operators, so that they give you an equivalent description of the primary ideal in the following way. So it's going to be all the polynomials inside this polynomial ring, so that when you apply each one of these differential operators in this list, then the result is inside the prime ideal. So indeed, he gave an equivalent description of any primary ideal with the use of differential operators. So Victor Palamudov, he is an analyst, and so he in his proof, in the original proof, he really used a lot the complex numbers and analytic methods. So as I said before, this bunch of differential operators, A1 until AT, they are called the Noetherian operators that encode the p-primary ideal. And this is interesting for at least two reasons. I mean, in its own right, it's interesting to describe primary ideals via because I mean, since Netter, any ideal has a primary decomposition, so they are basic building blocks. And from actually the interest or original interest of Palamudov is that this appears in the fundamental principle of Remprice of Palamudov when you want to solve any linear system of PDE with constant coefficients. Okay, so, but I want to recall just a little bit of history and concept because I find the history of this problem quite amazing. So the first one that studied this problem was Brogner in 1930s, and he showed that you can describe any zero-dimensional primary ideal with the use of differential operators. And of course, what he used was the Macaulay's inverse system. Then actually, during his whole career, Grobner was interested in this problem. And in a conference in Liège, he explicitly asked, okay, I can describe zero-dimensional primary ideals with the use of differential operators. What can be done in the positive dimensional case? This turned out to be a quite difficult problem. And actually, the ones that really pushed the problem forward were people in analysis, in PDE, in the fundamental principle of Remprice and Palamudov states that the solution of any linear system of PDE with constant coefficients can be represented in terms of center and interest. But surprisingly, the main step of this fundamental principle is actually describe primary ideals with the use of differential operators. Okay, so my goal is like I want to describe any ideal with the use of differential operators, but before I will recall some previous results of how to describe any primary ideal with the use of differential operators because this will be needed. So probably it's very well known for everyone in this session, but I will recall the notion of differential operators following Grothendieck is as follows. So the differential operators of the order 0 are linear differential operators, and then inductively the differential operators of order n are the ones that when you apply all the possible Lie brackets, they are a differential operator for the n-1. And then this is just a set of the whole bunch of differential operators is denoted like this. And then of course, if you are, for instance, in a polynomial ring over a field of characteristics, what you recover is the bialgebra. Okay, so my first question is what kind of differential operators can we use? So we saw that Palamudov, he used differential operators from R into R, so in the ring of differential operators to describe primary ideals. No? And then there is a very famous example by Bernstein, Gelfand, and Gelfand. And if you take this affine cone over this cubic, then you have that this ring of differential operator is famous, that is non-Noetherian. But actually what I want to use is that, as Josep in his talk was talking before, that the degree of a differential operator. So implicit in the proof, they show that there are no differential operators of negative degree. So there is no differential operator that can take an element of degree I and goes to an element of degree I minus 1. Okay, so using that there is no differential operator of negative order, you can show, for instance, that already in this setting, you will not be able to prove the original, you will not be able to extend the original theorem of Palamudov, because, for instance, in this really nice, simple ring or algebra, I would say, you cannot describe M squared with the use of differential operators. So what I mean by that is that you cannot find differential operators delta 1 until delta m, so differential operators from R into R, such that M squared will be described in the setting of Victor Palamudov. So you apply the differential operators and then it goes to M. So this follows basically from the fact that there is no differential operators of negative degree. Okay, and then one of my first result here is that actually it's in a quite more general setting, but let's take like this. So if you have K a field, R is an algebra of finite type, and P is a prime ideal, and again, Q is a P primary ideal, then we can find differential operators now from R into R mod P, so that you can describe any P primary ideal. And now the idea is that you really look this as a system of differential equations, I don't know how to call it, is that are all the elements in the algebra, so that the result is actually equal to 0. So this is a map from R into R mod P. So before, in the setting of Palamudov, if from R into R, so that the result is inside P. And then, of course, if the algebra is a smooth over K, then we have that you can recover the result or original result of Victor Palamudov. And the idea here, the trade-off between the two things is that this canonical projection induces a canonical map of differential operators, and typically this map is not subjective. So there are a lot more differential operators here that they allow you to describe any P primary ideal. On the other hand, if the algebra is a smooth over K, then this map is really subjective. So I forgot here to put is subjective. Sorry. So this is the first thing, that we can describe any primary ideal with the use of differential operators. Now let's describe any ideal with the use of differential operators. So it's the next step. Now for the rest of the talk, I will fix K is a perfect field is needed for the bounds that I will give. K is an algebra of finite type over K. I is any ideal, and I will fix the associated primes of this prime. So P1 until Pk. And now this is definition with Bern, Strumfels, and we say that the differential primary decomposition is a list of pairs, where the pair is just the second component. The second element is just the associated primes, and the first component is a finite list of differential operators from the ring into R mod Pi. And then what we want to do is like something like a local or shift theoretic definition, that we want to recover all the possible localizations of the ideal. Okay, so for each one of the associated primes, I will say that it's a differential operator if this list of pairs satisfies the following condition. So if you restrict to all the prime ideals inside P, because the other ones makes no sense. So if you restrict to all the prime ideals, all the associated primes that are inside E, now you want that the localization of those differential operators in the corresponding set of differential operators will give you that localization. I will not enter into detail, but it makes perfect sense to localize a differential operator, and that's not a problem. So the idea is that we want a notion that will recover for you the localizations of the prime ideal. So these things are unique. We are not doing it in terms of the primary decompositions, because it's well known that embedded components can be horrible, and that's not what we want. And actually, by recovering this like local version that we want to recover at all the possible localizations, we get some nice results, I would say. So this is our definition. So the definition is that we want to recover all the possible localizations of the ideals at all the associated primes. Okay, so basic fact that we can prove is that actually this local definition will recover for you the ideal. So the ideal will, because you can delocalize all this construction, is all the elements inside the algebra, so that the delta of f is equal to 0 for all the possible differential operators in all these possible lists. Okay, and then if the algebra is smooth over K, then we can take actually differential operators from R into R, because of the canonical map that I said before is surjective. Okay, and actually for the examples that I will show, I will make no difference, and I will always take differential operators from R into R because it will be just a polynomial ring case. Okay, now a basic fact is that actually differential operators, differential primary decompositions will always exist. This is basically a corollary of the previous result that I showed you before. So take a primary decomposition and now take a bunch of differential operators describing each one of the P primary components. Now you take each one of these lists and this gives you a differential primary decomposition. That can be checked easily, but really what we want to show here or is to see what's the minimal size, possible size of a differential primary decomposition. Let's see a simple example. So let's take this monomial ideal. And as I said before, since this is a smooth over K, I will basically take differential operators inside the Bilal algebra. Let's say, if we assume that this has characteristic 0. So this ideal has a primary decomposition, so ordinary primary decomposition of the following way. Now, we can show, even by hand in this monomial case, that, for instance, x1 to the square is going to be described as all the polynomials, such that when you apply the differential operator 1, so the element is inside x1, or when you take partial derivative with 1, then the result is in x1. So this is a description. So we say that 1 and partial x1 are Noetherian operators for this primary ideal. So you can do the same for the second. So you see here that for the second, the list is slightly bit more complicated. So now this gives you a total of 8 differential operators. So what I say here, this naive construction, which gives you a total of 8 differential operators. But actually, we can do a lot. We can do better, no? So we can actually describe this ideal with just 6 differential operators. So we can describe this ideal with the following 2 lists of differential operators. So for the minimal prime, we take 1 at partial x1, and for the other one, we can just the thing is that the information that these 2 differential operators are going to give you with respect with the embedded prime is already given by these 2 differential operators that were given before, no? Okay, so in actually we see here that the minimal description, we will see this later, that the minimal description of this ideal is actually with 6 differential operators and not with 8. And here it plays a role that we have an embedded prime. Okay, so the driving question that we were that was bugging us for quite a long time was how to minimally represent an ideal with differential operators, because this was already known from quite a bit of time for primary ideals. Okay, so and then our answer is the following definition, which is we call arithmetic multiplicity. And now here, this is a slightly different of the notion of multiplicity is that remember P1 until Pk are all the associated primes of the ideal. And then I'm going to compute the multiplicities in this sense. So you take the 0 local cohomology module, localizing at that prime, and you take the length. So in this ring is the length of the largest ideal of minimal length. So this thing, taking this 0 local cohomology tells you more or less that you're making some sort of saturation, you're deleting whatever information is redundant. That's the idea. A remark is that this arithmetic multiplicity is not the sum of the mix of the multiplicities coming from the primary decomposition, because here, for instance, in this case, you have that the multiplicity of this ideal is 2, and the one of this is 6, and we have a total of 8. But actually, we can compute that the arithmetic multiplicity of this ideal is 6. And actually, this notion of arithmetic multiplicity has a strong connections with many things. It's actually so if you assume that the ideal is homogeneous, and now in a polynomial ring, then there is the notion of arithmetic degree, which is exactly this notion of arithmetic multiplicity, but now you take products times the degree of the corresponding projective varieties, no? So it's like a adulterated version of arithmetic degree, and this has appeared in several works. So this name of arithmetic degree was coined by the work of Bayen and Mumford. It appeared in the work of Collar in some way in the effective Nussel and Sartz. in the connectivity of the Hilbert scheme by Hartshorne, and also some bounds that were given in a work by Strumfeld, Strum, and Vogel. So there is some connections between, yeah. So this is like the degree. So actually the arithmetic degree, and here we are dropping these degrees, and this is the arithmetic multiplicity. And then what we prove is that in this general setting, the size of any differential primary decomposition is at least the arithmetic multiplicity of the ideal. And this result is sharp. Actually, more precisely, we show that the ideal has always a differential primary decomposition where the size of the set of differential operators corresponding with the ideal is equal to this notion of multiplicity, which is the length of this zero local cohomology model. Of course, if the prime is a minimal prime, then this is just a regular multiplicity. And this is sharp, and this is the best that you can do. We prove also that actually a differential operator, a differential primary decomposition for I will always satisfy that the size of these sets is always at least this notion of multiplicity that I show you. Okay, so with this result, I think that it's fair to say that we can say that the arithmetic multiplicity of an ideal can be thought of as the differential complexity of an ideal. So to describe any ideal with the use of differential operators, using this definition that we have, the best you can do is the arithmetic multiplicity of the ideal. And I just want to mention that our result also covers the case of modules. So this result follows verbatim for the case of modules, but for the case of simplicity, I just talking about the case of ideals. I just want to give you another example. So because in this example is so you have here the two differential operators are repeated, and there's like deleting the two ones. So actually we have examples like the difference between the number that we have and the number. So the naive bound of summing the multiplicities of all the differential all the primary components can be arbitrarily different from the arithmetic multiplicity. So let's see this basic monomial example also. So we have this primary decomposition can be computed. The associated primes are x1, xy, yz, and xyz. So now here there are like three levels of embedded components. So this is the prime, so you need to just one differential operator for. So this is an Noetherian operator to describe this prime ideal. These two differential operators are needed to describe this primary ideal. So it's primary with respect to x and y. Here this is prime, and you only need one differential operator, so one Noetherian operator, and then you have this classical type of primary ideal that appear that is described by these differential operators that you have 1, 2, 3, 4, 5, 6, 7, and 8. So now this naive computation will give you that the size of a differential primary decomposition for the ideal will be of size 12. But actually, we have that the minimal differential primary decomposition for the ideal is given. So you take just one for the ideal, you take one. So you take one for the first component, you take one for the second component. So this guy is already relevant. You take only partial x with respect to the. Oh, I make things here up. So this is A3 and this is A2. Sorry. Okay, and then for A4, you actually just need two differential operators. This one and this one. So just bear in mind here that actually one primary component has more complexity than the whole ideal. So to describe this primary ideal, you need 8 differential operators. But on the other hand, the ideal can be described only with 5 differential operators. So what we are saying here that you can describe the ideal with these 5 differential operators, and actually you can compute that this is the arithmetic multiplicity. Yeah, so that was the last example that I want to show you. Thank you very much.
Thanks, Yairon. Are there any questions?
I have a question. So you said you guys showed that you proved that for each associated prime, you can come up the number of operators you need is,
yeah.
So is this constructive? Like, do you?
Oh, yeah. Actually, yes. You can try this in Macaulay 2 after version 1.17. I mean, I did not have time to talk about all this, but afterwards we joined forces with people from Atlanta, Anton Liking, and people from there, and we implemented the whole thing. And you give me just an ideal, and you type differential primary decomposition, and actually what I did here is I copy from Macaulay 2.
There. So it will give you exactly a minimal set of operators in you.
Yeah, and I should say that actually this set of differential operators are unique as vector space. So they are actually isomorphic in some sense, like taking a bunch of duals because differential operator is dual of module of principal pairs, whatever, but it's going to be actually isomorphic as a K-vector space to this zero local cohomology module. So, so I would say that one of the gains that we had taking this approach, I mean, with respect to the standard notion of primary decomposition, is that it's unique in a sense, because I mean, standard primary decompositions can be ugly, like the embedded components can be really ugly. Yeah, thank you.
Great. So really, so if I understood correctly, you're saying this multiplicity number is really the rank of this vector space given by.
Yeah, it's the dimension of this vector space. Yeah.
Great, thank you, thanks.
Yeah, thank you.
Oh, sorry, and you were saying there was a uniqueness type result even for the embedded components?
I mean, yes.
Okay. Oh, interesting.
I mean, so this has a structure of vector space over the residue field of the prime, and now what is constructed the proof. So the proof, what we choose is like of these vector spaces over the residue field, we choose a basis. So it's unique up to choosing a basis of, yeah.
Hello, can I ask a question?
Oh yeah. Hey,
so hey, nice talk. So my impression, you didn't talk about the algorithm, but to compute this differential decomposition, you need to pass through computing a primary decomposition. Is that correct? Or at least that's how you show.
No,
you don't. Okay, how do you do it?
No, actually, what that's one of the things that I should have said. Yeah. So actually, you can just take the ideal and you can localize.
Okay.
And the construction is directly from the localization of the prime ideal. So okay. one. I mean, I didn't speak about the algorithmic point of view of this, but one gain is that you don't need to compute the primary decomposition.
But I guess as an outcome of this, you may be able to reconstruct the primary decomposition, right?
Oh, of course, I can reconstruct it, the primary decomposition. So the only thing that we need to do is to pre-compute the associated primes.
Yeah. So the
that's
data is
cheaper than the other.
Okay, and I just another question is like, do you also? I mean, there is a characterization when the arithmetic, how do you call it? The arithmetic multiplicity coincides with the normal one. Is that?
What do you mean by the normal one?
Well, just a geometric multiplicity, for instance.
I mean, they will be the same, for instance, when the ideal is radical. But when the ideal is not radical, the two things are going to be, of course, different.
That's interesting. Thanks.
Thank you.
Are there any other questions?
Yes. Yairon, you think something like this can be done if the ring is, you are outside the polynomial ring, like you are like in a singular ring, let's say the simple? You think that you can find?
But the result is for any algebra of finite type over a perfect field.
Oh.
So the examples that I gave you, are like polynomial rings, just to show you. I mean, already this example is non-Euclidean. So, but this is for any algebra of finite type over any perfect field.
And over there is also constructible, the operators.
Oh, no. I mean, yes, in theory, yes, but the algorithm is only in Macaulay 2 is just for polynomial rings.
Okay. Thank you.
Any other questions? maybe let's thank Yairon again for a nice talk.
Thank you.